Hello, hello, hello. Good evening, everyone. Yeah. So this is week 7 discussion for the course Solar Photovoltaics Fundamentals, Technology and Applications, which is being taken by Professor Soumitra from Department of Physics, IIT Roorkee. And I'm Ravi Kumar, a PMRF research scholar at IIT Bombay. So let's start this week discussion. So in this week, what we have some peroxide material thing. What are the advantages? What are the disadvantages? And then we have a tandem cell structure. So as already we have seen, like we have gone through first generation, second generation. Now we are on the third generation. So we are focusing on the peroxide materials or peroxide solar cells. So like as I discussed in the last class as well. So just let me know what are the factors on which the efficiency of a solar cell is depends. On what factors does the efficiency of a solar cell depends? Write whatever is coming in your head, just write in the chat box. Band gap. Okay, I'll write here band gap. Stability. Does stability concern with the efficiency? Stability is related to the time. I'm saying just consider time zero. Absorption coefficient. Okay. Composition. Composition is a material property. So what factor it will give? Composition is a property. Morphology, yes. But morphology is giving our absorption coefficient. Yes, right. Output voltage. Yeah, Aruna, output voltage is a performance parameter. It is coming after the efficiency. It's like after making a device, it is coming later. So it is a derived parameter. It depends on some other parameters which we are talking about. Even output voltage we can say depends with the band gap. See, just learn to think what is going on. If it is a solar cell and sun is there and some intensity or like light is coming on the surface of a solar cell. So what should be the first phenomena? This light will go inside this material, and as it will go inside deeper and deeper, so this depth depends on absorption coefficient. So one thing we can say absorption coefficient. But what it is giving us? It is giving us generation. So first thing is generation of charge carriers. Think if there is a solar cell in front of you and it is working. So first it should absorb some light and then it should generate some charge carriers. Then what should be the next step? After generation, what should be the next step? Interface. Interface is not a phenomena. Interface is a physical. If there is charge carriers, let's say here we have electron and hole charge couple, electron and hole, then what should be the next phenomena? Yes, Chandan, you are right. Then after Chandan, Vinod, you are also right. So second thing should be dissociation, and third thing should be diffusion, we can say. And last, it's just understand this. This is the charge carriers being generated. Now, as Chandan said, there should be exciton dissociation. Yes, Vinod, you are right. So dissociation means they will be separate. So there will be electron and there will be hole. But just see, if this is a solar cell and this electron and hole are here only, they are dissociated, they are free charge carriers, but they are at a particular place. So they need to move or they need to diffuse. So they will go to the edge of the material. And then as Vinod said, there should be high collection or collection of charge carriers. Then fourth will be collection. So these four factors are very important to define the efficiency of a solar cell. If there is large generation of charge carriers, large dissociation of charge carriers, large diffusion of charge carriers, and large collection of charge carriers, then efficiency will be large. And if only one thing is less, let's say collection of charge carrier is zero, then efficiency will be zero. Even these factors are having high value, but collection is zero, so there is no use of these factors. So yes, exciton generation. Exciton means electron hole pair, then their dissociation, then diffusion and collection. So these are the four phenomena which are very important, which decides the efficiency of a solar cell. Understood? Okay, let's move to the next thing. What we have? Oh, same thing I am having here only. So behind this, there is a representation of these four things: generation, dissociation, diffusion, and collection, as we have discussed in the previous classes. Next, now we have talked on crystalline silicon, then amorphous silicon, then organic solar cell, then dye sensitized solar cell, and then perovskite material. Perovskite material is important to discuss, but why? What are the advantages these materials are giving us? Why we are focusing on peroxide materials? Can you name few advantages of this material? High efficiency. Yes, Vinod, you are right. Now let's talk with the parameters which is defining this efficiency. As we discussed in the previous slide, first thing we discussed, generation. Generation of charge carrier is associated with the absorption coefficient. So absorption coefficient for this material is high. Second thing we discussed about dissociation, and then we discussed about diffusion. So for this diffusion and dissociation, what we need, and even collection also, we can say collection. What is important? More diffusion length. Yes, more diffusion length. diffusion length. Diffusion length, and also we can say drift velocity, all things are related. Yes, mobility, drift velocity, and then like absorption coefficient, carrier lifetime, diffusion length, and mobility. So these are the advantages of this peroxide material. That's why this efficiency is high for the peroxide material. But if we are having high efficiency, then in the field as well, we are still using crystalline silicon. Why? The things I am talking about today, these things I already discussed in the previous classes, and this is just a type of revision. So what are the limitations which are a barrier for this peroxide solar cell to be implemented in the field? Why still we are using crystalline silicon in the field? Poor life, LYF, I am not getting what is this. Are you talking about life? Yes, you are right, but still you are, see, there are few things, and one thing is related to, and all decide the life. So you are talking about life, but there are few parameters which deciding this life. Yes, lifetime peroxide is 1 year. Yes, but life is a like broader term. On what factors does this life depends on? As we said, efficiency. So there are some parameters on which this efficiency depends on. On the same way, for this, someone wrote this, Haruna, break down quickly due to exposure of heat. Yes. So first thing, as Haruna said, so we can say exposure of heat, we can say thermal unstable. Yes. Sorry, second. Crystal lattice stability. Yes, stability, you are right. Instability due to moisture. Yes. So we know then, Chandan, your point are like right, and you are like saying the same point. So it is about the crystal lattice stability. And yes, you said moisture. So we can say moisture stability is less. Third, thickness issue. What is the thickness issue, Haruna? And does this thickness issue will decide the life? Yes, these things like film quality, thickness issue, life, these are broader terms. If any like material is thermally unstable, then we can say the quality is poor. I totally understood what you want to say. You want to say morphology is not good. Okay, let's consider one thing. If you have a solar module or solar cell working in the field, then what all the stressors it will have or it will face in the outside environment. Does it will it like feel heat? Yes or no? Yes. See, we are focusing on the stresses, those are available in the field, because at the end our material or our solar cell should work in the field only. So we will not say that a solar cell should be fire resistant, because it will not work in the fire, it will work in the outside environment. So just talk about the stressors which are available in the outside condition. What all stressors we have? Someone said thermal unstable. Yes, we have thermal cycling. Sometimes temperature is like 40, another time temperature is like 15 degrees Celsius. Moisture instability means sometimes we have 100% humidity due to rain. Sometimes we don't have, like on the sunny day we don't have humidity, but in case of rain some moisture can ingress inside the solar cell. So yes, moisture stability is important to discuss. Yes, high temperature, we already talk about this. What about gases in the atmosphere? Do we need to see if gases available in the atmosphere are degrading the performance of a solar cell? Does it is important? Yes. So air is also important to discuss. And one more important thing, if you are standing just outside during a sunny day, what will you feel? You will feel temperature and light. Light is important to discuss. So stability against the light. So these are the things we can say. Thermal stability leads to phase transition. Humidity stability leads to decomposition of the material. And then the light stability leads to diffusion. Diffusion means loss of charge carriers, high recombinations we can see. If recombination is high, then charge carriers collection will be low and efficiency will drop. So these are some problems with the peroxide material. Now let's move to the next set. So other than this solar cell, we have this peroxide material can be used in multiple applications. So we will just touch upon that. What are those applications? Can you name them? Just think, this material, photodetector. Yes, photodetector, we have laser. It's like this peroxide material is having some optoelectronic properties. So the device which need optoelectronic property, those devices can be fabricated with this material. And we have solar cell, photodetector, laser. Yes. So these are the applications. Optoelectronic means optical properties like light is giving some charge carriers. Yes, LED as well, giving some charge carriers. And see, this light is optics and this electron is electronic. So optoelectronic. So all these devices are optoelectronics, means they are dealing with light and electronics or electrons. Okay, so see, after this we have seen like crystalline silicon, amorphous silicon, then we have organic, then we have peroxide. So we have dealt with the old type of material for the single layer, but to increase the efficiency further, we need to do some more engineering. And like on this more engineering side, we have another type of solar cell that is known as tandem cells. Do you know about tandem cells? Anything? What is the meaning of tandem and all? Just write here. Yes, stacking we can say. Anything more meaning? Stacks of PN junction. Tandem means we are using multiple devices, multiple single solar cell. We are just making them tandem, means they are working with each other. Stacks of PN junction, yes. See, that's if this is a solar cell, NP multi-junction. Multi-junction is different thing. Multi-junction and tandem is different thing. See, I'll show you what is multi-junction. If this is a p-type semiconductor and I make n-type here and n-type here, how many junctions are here? One junction and two. So multi-junction device is like this. But tandem, it's like we have complete device, then we have complete device. It is a complete device with multiple junction. But in case of tandem, we have single device plus single device. NP. Yes. See, this is the picture of tandem solar cell. It's like this is cell 1, this is cell 2. Here also cell 1, cell 2, cell 1, 2, 1, 2. So we have one cell, then we have a tunnel junction, and then we have another cell. It's like we have one cell, then we have another cell. So if it is positive, it is negative, it is positive, it is negative. Means we are having cells in series in this first structure. And in the second structure, we have these solar cells like independently. They are not connected in series like this. If this device we can change, how? We can just use this positive, negative, then this positive and this negative. So we have 4 terminals here and we have 2 terminals here. So in case of a 2 terminals, our both solar cell are series already. But in case of this 4 terminal solar cell, those solar cells are not in series. But here we need more metallization as compared to this. It is just double. and the below picture are exactly same, just changing the direction of light. First light was coming on the upper one. Wait a minute, I think there was some issue with the internet. Am I audible to you? Just write in the chat box. Okay. Wait a minute. Yes, it is visible. Yes. See, what you need to understand in this tandem cell, Okay, I don't know, my camera is not working now. Okay, so in case of tandem cell, I was talking about there are two cells, cell 1, cell 2, and we are using them in tandem, means with one another. So there are many configuration. Configuration means we have cell 1, cell 2. So light can come first on cell 1, then it can go through the cell 1, and then light will go to cell 2. On the another hand, we can have cell 2 first, then cell 1. So light first will come on cell 2, then it will go to cell 1 after the transmission. So, and based on this, we can have like individual output of these solar cells, or we can have a combined output. So this combined thing, we have two terminal, and for the individual thing we have four terminal solar cell. Understood? Yes, no? Okay. So this is all about the tandem cell. Now there is a tandem configuration. In what configuration we can have these tandem cell? So it's like we have one cell, then second cell, and we are taking individual output. So total output will be P1 plus P2, as I talked previously. And in case of a single output like this, we will have same current because they are connected in series. So current need to be same and voltage will be added up. So this will be the power output for two terminal tandem cell configuration. And then we have a combined like series and parallel combination. For series and parallel combination, this will be the power output. And this is, there is a one more way we can have like one cell at a particular angle so that the light will be reflect and it will be captured by second cell. So this way we have different tandem configurations. Here, what is our motto? What is our objective? We can say to absorb more light. It will generate more charge carriers. That's it. It's like if we have some particular EG, so light having energy more than EG will be captured, and energy which is having energy less than EG band gap will pass through the device. So if light is coming on the surface, let's say some light is being absorbed and some light will be transmitted. So this transmitted light will be utilized by the other solar cell. So it will use this transmitted light, it will use the absorbed light, and they will both will give us a output, power output. Understood? Okay. Now we have some questions based on this tandem cell and like peroxide material. So first question says, what is the optical band gap of MAPBI3? And these are the options. What is the optical band gap? C. Yes, Vinod, C. C is the correct answer here. As you can see in this figure, it is, there are three materials, and for this iodine we have 1.53 electron. This is shown here. Now we have next question. which says the absorption onset for MaPbCl3, MaPbBr3 and MaPbI3 peroxide single is respectively, means absorption onset at which the light is being absorbed. Chlorine, bromine, iodine. Vinod said D. What about others? What do you think about this? Okay, based on this figure, you can say anything. Vinod, do you want to verify your answer? Just see for chlorine, bromine, iodine.
Option A is correct.
Yeah, option A is correct. For chlorine, we have around 440, then we have 570, then we have 850. So option A is the correct answer. Next question, it says the trap density in peroxide single crystal in the order of, these are the options. A, A. Vinod said A. Chandan also said A. Yes, A is the answer here. Next question we have, which is the example of transparent conductive oxide, which we have seen in last few classes?
A.
A. A is not a conductive oxide, A is a peroxide material. Yes, Vinod said B. Chandan said B. Yes. ITO. We were discussing many times ITO layer, and that is transparent conductive oxide. So answer here is B. Next question. We have nucleation without preferential nucleation sites is called. Vinod said A. Yes, A. No, not C. So this is the question about the relationship between diffusion constant D, mobility of electron, and these are the options. So it says Einstein relationship between the diffusion constant D and mobility of electron mu is C. No, Vinod said A.
D.
D. Someone said D. Yes, D is the correct answer here. It is just a relationship. Then we have slow cooling method of single crystal growth is based on the concept. And these are the options. Means what is the basic concept behind this slow cooling method? A.
It's B.
Does the solubility decrease with increased temperature or solubility increase with increased temperature? See, we are saying slow cooling. It's like let's consider it is a liquid and we have some nucleation here, some material, and temperature is decreasing. So to get a crystal structure around this thing like this, does the solubility should decrease or increase? Means the material from the liquid need to come out or it need to dissolve more and more? It need to come out. If any material from the liquid, from the mixture, will come out for a preferential nucleation, then only there will be a crystal structure. So this solubility should decrease with decrease in temperature. Then only we can get a crystal structure. Understood?
Yes, sir.
Yeah. So solubility decrease with decrease in temperature. Answer here is A. Next we have MaPbI3 peroxide has phase in temperature. Means there are two phases of this particular peroxide material. One where temperature is less than 160 Kelvin and another when temperature is between 160 and 327 Kelvin. And what are those phases? Is it cubic and tetragonal, orthorhombic and cubic, orthorhombic and tetragonal, cubic?
B.
C. Vinod said C. Orthorhombic and tetragonal. Yes, C is the correct answer here. So it is orthorhombic and tetragonal. It is the structure shown by this particular peroxide material. Next question is very simple. It says delta K value, difference in K value of valence band and conduction band for direct and indirect band gap peroxide is respectively, and these are the options. What should be the delta K value? Means K difference in the K value of valence band and conduction band for direct and indirect band gap. What is the answer here? Just remember the picture E versus K for the direct band gap and indirect band gap. Then you will get the answer. What is direct band gap? Okay, just have a look on this picture and let me know the answer.
Valence band and conduction band are aligned in the case of direct.
Yes. So this is direct band gap structure and this is indirect band gap structure. So what about the K value? If they are aligned, then the difference in the K value should be 0. and
Zero.
here it should not equal to 0. Then which option is correct?
B.
B or C? Yes. For the direct band gap, it should be 0. Oh, okay. So it is first is direct and then indirect. Yes, B.
So it's B.
Yes. So B is the correct answer. Let's move to the next question, which says which one is not the type of tandem configuration? And these are the options. And we have discussed all the three, and one which is present here we haven't discussed yet. So that is not a tandem configuration. D. Okay. Yes, this is 4 terminal, this is 2 terminal, this is series parallel. Yes, Chandan, it's D, 6QT. So D is the correct answer. Next, we have a small numerical and you need to solve it. And it says a single solar cell 10 centimeter into 10 centimeter produces a voltage of 0.5 volt and current up to 2.5 ampere. If the solar insolation is 800 watt per meter square, the efficiency of the solar cell is. Solve it and let me know the answer. Very simple question. If you have any doubt in the numeric or sorry formula, you can ask. So in the next class, we will be having some characterization techniques. So till now we have completed all about the solar cell. Just solve this numerical. Very simple numerical. Someone said answer is D. Let me solve as well. What are the things? No, D is not the answer. D is not the answer. A. Okay. Yes, someone want to ask? Anything? P out, P in. Okay. Yes, your formula is right, but there are few things which you are not asking, which you should ask at least. How many voltage and current correspond to a solar cell we have in a solar cell characteristics or IV characteristics? I think you have do not remember this. This is the IV characteristics of a solar cell. This is voltage. This is current. So what is this point? This point. What is this point? Don't you remember? And what is this point? What is this point? What is this point and what is this point? I marked 5 points here. I'll write A, B, C, D, and E. What is A, B, C, D, and E? What is A? What is B? Don't you remember the IV characteristics of a solar cell? I hope you do. A. Vinod said answer is A. Okay, Vinod, just focus on this thing. The IV characteristics I have drawn. Yes, someone said ISC, but which point is ISC? A, B, C, D, or E? A. A is ISC. What about B? B is VOC. What about C? C is MPP. So we can say P MPP. What is D? This is D. D will be at VMPP and E will be IMPP. For the efficiency, we have fill factor into VOC into ISC divided by insolation into area. Or same thing we can write IMPP into VMPP divided by I into A. So how do you know this voltage is which voltage and this current is which current? Did you ask it is VOC, ISC or VMPP or IMPP?
It's a VMPP.
I'm asking how do you know it is VMPP? Okay, so you have calculated 15.6 while considering it VMPP and it IMPP. Now let consider these values at VOC and ISC. Now calculate. Can you calculate it? You are right. These are VMPP and IMPP. But why you are right? Now try to calculate efficiency of the same question while considering the given voltage at VOC and given current as ISC. Can you calculate it? Why not?
It should it should be less than that.
It should be less than that. Totally agree. But can you calculate this? Yes, fill factor is not given. And fill factor is not given, then you consider it is VMPP and IMPP. Yes. Yes, you are right. This is the answer. Okay. Let me give you fill factor now. You all are right. Your answer is correct. I was just telling you before considering which voltage it is given, which current is given. You just think more about this. Now let us consider fill factor to be 78%. Now calculate efficiency while taking VOC and ISC. I have given fill factor at 78%, 12.68. Okay. Okay. It should be 12 point something, yes. So yes, while considering VMPP, IMPP, answer is A. And this is the last question for today. It says solar insolation on a rectangular module. It is saying module 1.5 meter into 2.5 meter of photovoltaic cell is 550 watt per meter square. If the efficiency of solar cell is 12%, what is the power output of the module? And these are the options. Calculate it. I'm sorry, my internet connection is weak today. Yeah, I'm sorry, there is issue with the internet connection. Yeah, I'm sorry, there is an issue with the internet connection. D. Yes, we know the answer is D. I'm trying to connect my other device. Yes, this was the question we were discussing about. Yes. So it says the solar insolation on a rectangular module 1.5 meter into 2 meter of photovoltaic cell is 550 watt per meter square. If the efficiency is 12%, what is the power output of the module? Yes, we know the right. P out equals to P in into or P input into area into efficiency. And answer is 198 watt, right? Is it 198, right? Yes. Okay. So that's it about today. So in the next class, we will be discussing some characterization technique related to this solar photovoltaic solar cells or modules.
Thank you very much, Ravi sir.
Yeah, you are welcome. I'm sorry there was some internet connection in the between.
No, no, it's okay, sir. No problem.
Yeah. Okay. Thank you, everyone. So next class will be our last class. Okay. So I'm ending this class. You may leave. Have a good day. We will meet in the next class. Yeah. Hi. Yes, definitely. So this is one is my email ID. Okay, I'm ending this class. If still you have any doubt, you want to ask anything, you can ask. If no, then you can leave.